A warm welcome, a very good morning, good afternoon, good evening to all of you wherever you are undergoing this course, taking this course. And as you know, this is the DADM, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series, and this course we have already completed 10 lectures, which is 2 weeks is already complete. Now, this total course duration is for 12 weeks, contact hours is 30, which when broken down into lectures is 60 in number, and each week we have, so that means each class is for half an hour. So, they are on roughly on the tune of about 29 to 30 minutes, and each week we have 5 lectures. So, with the completion of the 10th lecture, 10 lectures in total. So, you have already would be in a position to take 2 assignments. So, after each week, as I said, there are assignments. So, hence after the end of the course you will be doing or completing 12 assignments plus 1 final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are discussing a very simple problem of 2 machines, 2 jobs, and each machine has 8 hours in each day considering one shift, and the number of hours required for to process product 1 or product 2 in machine 1 and machine 2 were given. And there we were basically formulating a problem with an idea that you want to optimize the total output considering the revenues are given, such that you can understand that revenues give us the information about trying to about the profit. So, you want to basically maximize the profit. Now, if you remember, I also mentioned at the fag end of the last class, 10th class, it was basically that each of the constraints are such that they would be met in totality, or some of the overflow would be there. Overflow in the sense some unutilized number of hours would be there for machine 1 and machine 2, considering the fact that the number of units to be produced at each end need not be an integer, but technically that we need integers because you are producing products. So, they cannot be 2.5, they cannot be 1.32. So, they have to be integer values, and these are greater than 0 because you cannot produce negative values of any product. So, this is, as I said, this is the 3rd week starting and we are in the 11th lecture. Now, whenever we are trying to consider this problem, so I will again repeat few of the assumptions which we will be encountering time and again. So, they would be the concept of proportionality. So, economy of scale. So, the more you produce, more you gain. So, obviously, in that case we will consider the proportionality having to be there in such a way that it is linear in nature. It is not increasing at an increasing rate, not increasing at a decreasing rate. That means, if you produce more and more. So, in that case the profit would not be increasing in a more than exponential manner, in the sense that if I produce 2 units I get a profit of 4, if I produce 3 units I get a profit of 6, if I produce 4 units I get a profit of 8. So, but in case if it is increasing at an increasing rate, which means that more I produce. So, if I go to 5 rather than 10, it will be, say for example, something more than 10, 11. When I produce 6 rather than 12, it will be, say for example, more than what it should have been, like 12.5. When I go to 7, it is not 14, it is, say for example, 15. And another case, when I consider that it is decreasing, in that sense, the decrease would be such that rather than 6 producing a output of 12, it will be less than 12. Rather than 7 producing an output on the profit output of 14, it will be less than 14, but the proportionality will be decreasing. We will also consider that the marketing efforts would be such so that the overall average return which we will get from the production would be positive in the sense it is increasing proportionally, it will be positive, such that any utilization or non-utilization would be coming out from the constraints, and they would give us the concept of shadow price and the slacks. Additivity would mean that if any complementary product is added, or if you remove one product and add another one, certain that one product can replace the other. So, in that case the constraints of the would be changed, but considering the fact that the proportionality and the overall feasibility of the feasibility means of the solution. So, obviously, the solution overall area would change, solution set would change, but the feasibility would remain such that we are able to find the optimum solution as required. We will also consider, again I am repeating, certainty of the values, no stochasticity, no uncertainty. That means, once given the data, we will proceed considering that it is the true values based on which we will do the calculation. So, obviously, it would not mean that as the production increases, the number of hours which is available keeps fluctuating over and below 8, or say for example, if the price fluctuation, if it is 1 or 2, or the number of hours required for machine for one product in machine 1 or machine 2 is 2 or 3, whatever it is, those values of 2 and 3 would not be changing randomly with respect to some distribution. So, once finalized, they will be fixed. Similarly, the cost structure, if you sell one product and the overall profit which I am going to get from product 1 is 2 rupees or $2 per unit sold, it would continue to remain as 2 rupees or $2 as we increase or decrease the number of products which are being sold for decision variable 1 or decision variable 2, as the case may be. So, certainty would mean the stochastic business environment, price and cost may vary in future, but we would not consider that. So, as I said, the cost structure would be the input cost, the raw material cost, the labor cost, the electricity cost. So, we will consider them to be fixed, we are not considering them the varying. In the same way, price, selling price based on which we are selling in the market, hence the revenues would be, the total profit would be selling price by the cost price, those would not be changing randomly, we will consider them be fixed and then continue solving the problem accordingly. This concept of divisibility would be the integer decision variables. So, number of peoples to be employed, or say for example, number of machines to be utilized, or say or number of trucks to be employed to transport goods, or the number of products to be made. So, in the initial problem I mentioned that the number of products which are to be bought and to be produced are all integers, but in the problem solving when you solve, you will find out they come to be non-integer values. So, technically this is also a very big assumption we will be considering to solve the problem, and later on we will see when we solve the integer programming problem, how this problem can be basically compensated in order to find out the best solution which will give us integer values without compromising on the constraints. So, say in this case we see that it is integer values, but say for example, on the other hand we are considering the problem of trying to mix paints to produce some liters of paints. So, consider there are 2 paints and with that they are the decision variables x1 and x2, but in this case paint amount of paint sold or bought or which is the decision variable can be in decimal also. It can be say for example 2.32 liters, it can be 3.996 liters. So, in that case we will consider continuity to be there such that the values can be considered as continuous. So, any variable would be possible x greater than equal to 0. Now, consider, so I will come to the, so that was the general feel of our 2-dimensional problem. So, I will consider again consider a second problem and try to basically give you a pictorial idea that how the problem is to be tackled or what is the conceptual framework of the problem. So, Asian Paint produces both interior and exterior paints from 2 raw materials. So, raw materials can, whatever the raw materials can be, they can be paint by itself, they can be some oil which is to be used, some chemicals to be used. The following table which is below shows the basic data. A market survey indicates that the daily demand for interior paint cannot exceed that of the exterior paint by more than 1 ton. That means, the demand between them is such that the demand on the interior cannot exceed that of the exterior by more than 1 ton. So, it has to be limited by that. Also, the maximum demand on interior paint is 2 tons in a particular unit time. So, Asian Paint wants the optimum product mix in order to basically find out what is the profit, considering the profit is a factor. So, let us consider the overall picture. So, let us go one by one. So, if I consider raw material 1, which for our case I am telling you beforehand is basically decision problem x1. So, number tons of raw materials required per ton of exterior paint is 6. So, this is I will not highlight, I am just try to basically make a note of that to all the students who are watching this video. So, raw materials required for which is of type 1 would be 6 tons to produce 1 ton of exterior paint. Similarly, raw materials required per ton of interior paint to be manufactured is 4, and the maximum daily availability in tons for raw materials 1, which again I am saying will be or maybe our decision problem 1 depending on how the problem has been formulated, is 24. That means, you cannot utilize more than 24 tons of raw materials 1. It can be 23.9 whatever it is, but obviously in that case there would be some leftover. So, what is the concept of leftover? I am going to come to that within few minutes. Now, for raw material 2, similarly the tons of raw material 2 required to produce exterior paint, 1 ton of exterior paint is 1 ton, that means 1 ton is required for raw material 2. Similarly, for raw material 2 which is required to produce 1 ton of interior paint, so that quantum is 2 tons. Again the maximum availability of raw material 2 given per day or per unit time is given as 6. So, these are basically the so called the constraints which you have corresponding to the fact that the availability in tons is given, some value is given in not in rupees, but in kgs or tons or liters whatever, in this case it is tons. Now, in this problem, remember in the initial problem we had done, it was basically producing products, that is why I kept mentioning it that the numbers have to be integers even though the formulation was not in that line, in the sense that the answer could have been say for example 2.3 number of product 1 or 3.29 of product 2, but I also did mention that we will be considering that in the later part when we solve the integer programming problem. But in this case it is, as I said, it is paints, hence the number of tons or number of liters, number of kgs can definitely be non-integer values, and they can be in decimal places also. Hence, trying to solve this type of problem using using linear programming would make much better sense. Not that we cannot solve the problem in the initial case using linear programming, but obviously there would be some caveats, some important points to be noted, which I mentioned accordingly, that the integer values would give us some excess amount of either or time left for machine 1 or machine 2, and the case may be. Now, coming to the cost factor or the profit factor or the revenue factor, in the initial problems it was the revenue. So, you wanted to maximize it. In the same case that it is given for this problem on the Asian Paints, it is profit per ton and it is given as 10,000. So, for selling exterior paints it comes out to be 5, selling interior paints it comes to be 4. That means, if you sell 1 ton of interior paints you get a profit of 4. I am only talking about the units, I am not multiplying it to 10 to the power 1000 or whatever it is, and selling exterior paints would basically give you a profit of 5 per ton. Now, consider the values to be decision variables to be considered. Now, remember one thing, the choice of decision variables for these problems have to be thought out very carefully, because the answer is that what they can be two ways of tracking the answer. Number one is that the amount to be produced is amount of paints to be produced would depend both on the exterior paint and the interior paint plus on raw material 1 and raw material 2. So, we will consider here x 1 as the tons of exterior paint produced daily, and similarly on the other lines we will consider x 2 to be the tons of interior paints produced daily on a unit time scale. So, in that case if you are considering the profit, remember, because you have to basically do the profit, in that case the profit comes out to be 5 into x 1 plus 4 into x 2, considering 5 and 4 are the respective values of the addition of profit for 1 ton of exterior paints and 1 ton of interior paints respectively. Now, coming back to the formulation which we need for the case of the constraints. Now, watch here very carefully. We assumed, and let me go back to the last slide. So, this will give a good picture. As per the problem formulation, it is said that you will need 6 tons of, say for example, tons of raw materials required for ton of exterior paint. It was 6 for raw material 1 and 4 for raw material 1 for interior paint. Similarly, the values corresponding to raw material 2 were 1 and 2, and the maximum value available for raw material 1 and raw material were 24 and 6. Now, we have considered the decision variables as exterior and interior paint. So, if that is the case, the constraints would be formulated as shown here, and if it is not that, if the decision variables was something else, then the constraints would have been formulated a little bit separately, which I will come to that within few minutes. Consider the constraint. So, okay. So, we have already considered the maximization objective function. So, I will highlight it. So, this 10,000 is because per unit 10,000 was the addition. So, it was 5 into 10 to the power 4 and this was 4 into 10 to the power 4. That is why this values of 10,000 is coming. Now, let me highlight constraint 1. Now, constraint 1 means we already know 24 tons is the limitation. Now, if I go into the utilization of material 1, we know that per ton of exterior and interior paints which we need 6 and 4 quantum of material 1 only. So, that means the total amount of material 1 being utilized to produce x 1 amount of exterior paint is 6 into x 1, which is the first value. So, that is the total, and the total quantum of exterior paint needed to produce the raw material 1, sorry, raw material 1 needed to produce the interior paint is 4 into x 2, because x 2 is the value of interior paints we are going to produce. So, if I consider the total utilization of raw material 1, it will be 6 into x 1 coming from exterior paint and 4 into x 2 which is coming from interior paint. So, the summation of that obviously we know has to be bounded by 24, hence the first constraint basically makes sense that we are utilizing the decision variables as in this interior paint and exterior paint, but we are trying to basically formulate the constraint based on the fact that the raw material utilization of 1 is important and given to us. So, this is the important fact. In case if we had taken x 1 and x 2 as the raw material 1 and raw material 2, in that case the problem formulation would have been different, because in that case the objective function would also change, similarly the constraint would also change. So, in that case the constraint utilization would have been based on the fact that if we are using x 1 amount of, say for example, raw material 1 for exterior and interior, then the proportionality would be divided accordingly such that x 1, the amount which you are utilizing would be less than 24, and similarly if you are using x 2 as for raw material 2 would be less than equal to 6. But again going back to the initial idea of trying to consider that what is the decision variable is exterior paint 1, exterior paint 2, which is x 1 and x 2. Let us come to the constraint 2 based on the fact that is important for raw material 2. For exterior paint, raw material 1 needed is 2 needed is 1 ton per 1 ton production. So, it will be x 1 amount needed for raw material 2. Similarly, for raw material 2, the amount needed for the interior paint is 2 tons per 1 ton of interior paint produced. So, if the total amount of interior paint produced is x 2. So, hence the total amount needed for raw material 2 would be 2 into x 2. So, the total now utilization of raw material 1 would be x 1 coming from exterior and 2 x 2 from coming from interior. If you add them up, obviously the total sum cannot exceed 6. So, that basically satisfies the constraint number 2. So, let me highlight it. The third and fourth constraint which have been mentioned when the problem was being formulated. So, there were some concept related to what is the total utilization of exterior paint 1, what should be the total combination of interior paint 1 and exterior paint 2, or the raw materials or of exterior paint 2. So, based on that, let us check what are the third and the fourth constraints. I will highlight it blue color. Now, remember here, if I take x1 onto the right hand side, it means that x1 is for the exterior one. So, the summation of x1 plus 1 additional ton which you produce should always be greater than equal to x2, considering x2 is basically being utilized for the interior paint being produced by Asian Paints. So, what does it mean? If I go back to the initial formulation, it mentions very clearly. I will use the same color to highlight. So, a marketing survey indicates that the daily demand for interior paints cannot exceed that of exterior paint by more than 1 ton. So, when I basically bring it in the formulation, this would mean that minus x1, I am just taking it to the left hand side, minus x1 plus x2 is less than equal to 1. So, this is the third constraint. So, the constraints would basically give you the idea that what is the overall feasible set. I will use say for example, red. Now, coming to the fourth constraint. So, it gives you what x2 is less than 2. So, x2 is what? x2 is the interior paint, less than 2, that means we cannot produce more than 2. So, does it come out from the problem formation? Let us check. I will use the same highlighting red in order to highlight that point which has been given in the problem. Here it mentions the maximum demand of interior paint is 2 tons, that means the total amount of being produced for interior paint cannot exceed 2. So, that point which is being highlighted in red color is easily discernible in the constraint. Now, if I see the constraint, there are 4 constraints, that means there are 4 equations. Now, what is the dimension of the problem? There is 2, because we have only exterior paint and interior paint and raw materials 1 and 2. Now, the problem of the dimension comes out from the decision variables we are producing. Now, look, let us think it very rationally. In case if the utilization of raw materials was more than 2, but still we had two exterior 2 paints to be produced, exterior and interior by Asian Paints, then only the number of constraints would increase, not the decision variables, based on the fact that how we have been able to basically utilize this in the problem. But if you formulate the problem in the sense where you will take the decision variables as the raw material used. So, in case we have 4 raw materials, in that case the decision variables will be 4 and the problem has to be solved using simplex method. Hence, trying to basically draw it in a 4th dimension would not be possible for us to visualize how it problem looks. But on the other hand, considering the number of raw materials being utilized is 2, but the output which is exterior paint 1 or interior paint 1 is there are now say for example 5 paints, paint 1, paint 2, paint 3, paint 4. So, in that case the constraints remains 2 in this case, because there are only 2 raw materials, but the decision variables corresponding to the fact that we are considering x1, x2, x3, x4, x5 as the paint we produce would basically change the problem how you are going to formulate. But for the same problem which I just mentioned, if I reverse the idea of the decision variables, right, rather than taking the decision variables as the paints produced P1 to paint 1 to paint 5, we take it as the raw materials which is only 2, in that case again the problem comes back that we basically have a 2 dimensional problem. So, how you formulate the problem is basically to be inculcated as you solve more and problem. So, there is nothing say straightforward technique which I will be basically able to give it to you, that how you will basically solve the problem as you proceed. But the actual algorithm, once the problem is formulated, so the main formulation would be important, how the problem is formulated, how you solve would be much easier, and that we will discuss. So, in this space, coming back to this problem, we had 4 constraints, 2 decision variables. The first constraint is related to the total amount of utilization of raw material 1, which is the orange one. The second green constraint is basically corresponding to the fact that we are trying to basically utilize the constraint based on raw material 2. The third, which is this is the green in color. The blue and red are the respective constraint corresponding to the fact that how the relationship between paint 1 and paint 2 and the maximum utilization of one of the other paints is being given in the problem formulation. The last one, which is very intuitive and very easy to understand, is that amount of paint produced of type 1, type 2 or exterior interior obviously is positive, hence x1 and x2 is greater than 0. Now, this I am repeating it, please bear with me, I am sorry for that. This x1 and x2 being greater than 0 was in the initial problem also, where we are basically trying to produce number of products, but in that case x1 and x2 had to be integers. Here there is no such bounding, conceptually or practically that would not be a problem. So, what we will do? We will basically plot the constraints. So, there are 4 constraints, we will plot it and check how they look like. We will identify first the region satisfying the constraints, because the constraint, each of the constraints have to be satisfied in order to solve the problem. So, those would be the total set of solutions which is applicable to be taken up for by us for the solutions. We will also plot the objective function for the 2 dimension one and check that at what point the objective functions leaves the overall the constraint space or the feasible space, in order to give us some idea where is the maximization or the minimization happening. We will also understand that where the decrease and the increase happens, in what rate and in which direction. So, why the decrease or why the increase? Decrease would be the point when we are considering the point of view from the minimization problem, and increase would be from the point of view of the maximization problem. We will identify the maximum value of the objective function under those constraints, and also consider the problem that this objective function once maximized would also be applicable to at that point, which will be given by the values of the decision variables, such that those values of the decision variables are the optimum value of x1 and x2, which will give us this answer. So, the problem basically when we consider, so in this case we basically, now going back to the initial problem, the first one, that was the 8 number of hours which was applicable for machine 1 and machine 2. So, you will want to maximize 3x1. I will come to this problem for Asian Paints within this class or the next class. So, you want to maximize the objective function, which was trying to basically produce number of product 1 and product 2, considering 8 number of hours was fixed for machine 1 and machine 2. Now, before I solve the problem, look at the constraints. So, if I put the equality sign, what it is? It is 2x1 plus x2 is equal to 8, and another constraint is x1 plus 3x2 is equal to 8. Now, less than 8 would be possible when I put 0 onto the left hand side of both the equations. So, obviously 0 is zeros in both equation 1 and equation 2 is less than 8, which means the origin, we are now sure that the origin would be lying onto, if I am considering from my point of view, it will be lying onto the left of the equations. Hence, we know that in which direction the feasible set will occur. And obviously, another constraint would be x1 and x2 is greater than 0. So, very simply, if I draw, consider this is the axis, I will go into the actual diagram later on. X1 being great, and consider this is x1, this is x2, x1 greater than 0 would be the it will become cluttered. So, I will just mark it very. So, this is for x1. So, all these regions, obviously it would be in this region also. So, technically anything above. When I consider x2 is greater than 0, so let me use a different color. So, obviously these values would also come. So, first and second for quadrant for x1 and first and fourth for x2. So, now the common area between them is only the first quadrant. Now, plotted this equation. So, I only plot one and I continue the other one. So, if I consider x2, I will use another color, let me use the blue one. So, if I consider x2 as 0, so x1 is basically 4. So, let us consider 1, 2, 3, 4. And if I consider x1 as 0, x2 would be 8. 1, 2, 3, 4, 5, 6, 7, 8. So, if I consider the line, so any part onto the left, because 0 was important for us. So, any part onto the left is applicable. Finally, when I plot the third one, so like third one, yes, I am taking this third one. Let me use the color, say for example, orange. So, when x2 is 0, x1 is 8, 4, 5, 6, 7, 8, and when x2 is 0, no, x1 is 0, x2 is 8 by 3. So, we will consider it to be, say for example 8 by 3 would be 2.23. So, 2.23. So, it will be somewhere here. So, if I consider, so again this portion below. So, technically if I consider, I will use another black color in order to make it very simple, or I will use the highlighter blue color. Let me use the yellow one. So, the overall space comes out to be, this I have tried to draw it very simplistically. Obviously, in 2 dimension, 3 dimension, the conceptual idea will be coming up later on. So, I will continue solving this problem in a very simplistic manner, and then basically give you a picture that what is the concept of feasible region, slack, in which direction the solution moves, in order to give us a good idea that how the LP formulation works in a very simplistic manner. Have a nice day and thank you very much.